Welcome to this explainer. Today, we're tearing down the math behind quartile deviation. You know how messy real-world data gets, right? Well, if you've ever looked at a chaotic dataset and wondered how to find the reliable spread, completely ignoring those crazy outliers at the very top and bottom, you are in the exact right place. We are going to demystify this step by step, and it is beautifully logical once you see the mechanics behind it. Let's get into it. Okay, let's just dive right into our roadmap for today. First, we'll define quartile deviation. Then, we'll solve it for individual series, discrete series, and continuous series. And finally, we'll wrap up with the interquartile range.
All right, part 1, defining quartile deviation.
Here is your absolute anchor for this entire explainer. Quartile deviation, or QD, equals Q3 minus Q1 all divided by 2. That's it. That's the master formula. Literally the whole game here, no matter how complex the data looks, is just figuring out how to find Q3, the upper quartile, and Q1, the lower quartile. Once you've got those two numbers, you just subtract them, cut the result in half, and you're done. Keep this formula in the back of your mind as we go.
Moving on to part 2, solving for an individual series. So, an individual series is basically just a raw list. Think test scores or ages listed out one by one. Here, n is simply the total number of items you've got. To find Q1, you plug that count into a really straightforward formula. N plus 1 divided by 4. But hey, remember, this gives you the position of the term, not the actual value. It's telling you to count down to the n plus 1/4 spot in your sorted list. For Q3, same exact logic, just multiply that position by 3. Find those spots, grab your values, and boom, you're ready for the master formula.
Let's level up a bit. Part 3, solving a discrete series. Now, things change slightly when your data groups into frequencies, like say 5 people scored an 80 and 3 people scored a 90. Before you even think about doing any math, data organization is absolutely crucial. You must construct a cumulative frequency table first. You'll usually see this called a CF table. You're basically just keeping a running total of your frequencies row by row. Oh, and n has evolved here. N isn't just counting the rows anymore, it's now the sum of all those frequencies combined.
But here's the payoff for building that table. Look at this! The next steps are exactly the same as the individual series. Q1 is still the n plus 1 over 4th term, and Q3 is still the 3 times n plus 1 over 4th term. It's repetition with a little variation. The formula hasn't changed a bit. The only difference is how we define n and how we hunt down that final position using our shiny new cumulative frequency table.
Okay, pause for a second because we need to explicitly contrast the logic here before we tackle continuous data. This is where a lot of people trip up, and I want to make sure you don't. Up to now, for individual and discrete data, we've always added a 1, right? It was always n plus 1 over 4. But as we transition into continuous ranges, like classes of 20 to 30 or 30 to 40, that plus 1 entirely disappears. For continuous series, you just use n over 4. Lock that distinction into your memory right now. Which brings us to part 4, solving a continuous series. Keep your energy up, you totally have the tools for this.
I know, this looks like absolute alphabet soup right now. But let's just preload these variables together so it's not overwhelming. Think of this like prepping your ingredients before you cook. L1 and L3 are just your starting numbers, the lower limits of whatever class your quartile lands in. N is still your total sum of frequencies. CF is the cumulative frequency of the class right before yours. F is just the frequency of your specific class. And C, that's your class interval size. So if your class is 20 to 30, your C is 10. That's it. Pretty simple ingredients, right?
Now watch how beautifully these ingredients snap into our interpolation formula. For Q1, you take your starting point, L1, and add a fraction. That fraction is your target position of n over 4, minus the cumulative frequency, all divided by your class frequency, F. Then multiply that whole chunk by your class size C. For Q3, it's the exact same mechanics. You just swap L1 for L3 and use 3n over 4 for your target position. By just plugging these pieces in, you can precisely extract Q1 and Q3 hidden inside those continuous ranges.
All right, final stretch, part 5, the interquartile range.
Remember our master formula from the very beginning? Quartile deviation was Q3 minus Q1 divided by 2. Well, if you want to find the interquartile range, or IQR, you literally just drop the divided by 2. It's simply Q3 minus Q1. The interquartile range represents the exact distance between your upper and lower quartiles. By removing that division, you're looking at the absolute spread of the middle 50% of your data, completely bypassing those extreme highs and lows.
So let's take a step back and ask, how does isolating and measuring just that middle 50% actually change how you view messy everyday statistics? Because whether you're looking at housing prices, test scores, or income levels, tools like the interquartile range and quartile deviation let you slice right through the noise of crazy outliers. They help you find exactly where the true, reliable heart of the data really beats. I really hope this explainer empowered you to look at data sets with a little more confidence. Thanks so much for hanging out with me, and keep exploring.